Calling an unsafe function or method. The second type of operation that requires an unsafe block is calls to unsafe functions. Unsafe functions and methods look exactly like regular functions and methods, but they have an extra unsafe before the rest of the definition. The unsafe keyword in this context indicates the function has requirements we need to uphold when we call this function, because Rust can't guarantee we've met these requirements. By calling an unsafe function within an unsafe block, we're saying that we've read the function's documentation and take responsibility for upholding the function's contract. Here is an unsafe function named dangerous that doesn't do anything in its body. Okay? Basically what they're stating here is that if you write an unsafe function or method, one is going to have the unsafe keyword, like this example here does, and two, you can only call that within unsafe blocks, like they did here. And then this is the example of just dangerous function that does nothing and calling it. We must call the dangerous function within a separate unsafe block. If we try to call dangerous without the unsafe block, we'll get an error. And let's test that out real quick. So copy this, editor. We don't need you anymore. Could format. So the first case where we call it within a safe block, unsafe block. No compile error. And now let's get rid of the safe. Let's get rid of the unsafe. I keep switching those words. Format it again, and let's see this error. Call to unsafe function. That's explicit. And it looks like the error is exactly the same, so I can just read it here. Call to unsafe function requires unsafe function or block. Okay. Oh, so based on what they stated here, you can do it within a unsafe block, or you can call an unsafe function within another unsafe function, which makes sense. By inserting the unsafe block around our call to dangerous, we're asserting to Rust that we've read the function's documentation, we understand how to use it properly, and we verify that we're fulfilling the contract of the function. Bodies of unsafe functions are effectively unsafe blocks. So to perform another unsafe operation within an unsafe function, we don't need to add another unsafe block. So yeah, this is what I got from the error message. They're just stating that if you have an unsafe function, within that unsafe function, you can call another unsafe function. It's already all unsafe. So you're good. Creating a safe abstraction over unsafe code. Just because a function contains unsafe code doesn't mean we need to mark the entire function as unsafe. In fact, wrapping unsafe code in a safe function is a common abstraction. As an example, let's study a function from the standard library split at mutable that requires some unsafe code and explore how we might implement it. The safe method is defined on mutable slices. It takes one slice and makes it 2 by splitting the slice at the index given as an argument. Listing 19-4 shows how to use split at mut. Alright, so we have a vector using the macro to create it, 1 to 6. We are assigning it to R, which R is not mutable, but the vector is. Okay. And then we let AB equal split split at mute 3, which then gives us the first 3 and the second 3. So this is how to use the split at mute. We should probably test this out just to make sure it works the way they told us to. So let's open this up. Get rid of dangerous. Format. Run. So that works. I guess the only thing that's sort of weird for me is this line. The let R, which is not going to be mutable, be a reference to this mutable thing. And then we're using R to split at the mutable point. That just seems awkward to me, but I guess I'm just not familiar enough with the language for that to sink in immediately. Oh well, moving onward. We can't implement this function using only safe Rust. An attempt might look something like listing 19-5, which won't compile. For simplicity, we'll implement split at mutable as a function rather than a method, and only for slices of I32 values rather than a generic type T. Okay, so they're saying this is not going to work, but we're going to simplify the problem. We're going to make it into a function instead of a method, so we don't have to have a struct and yada yada yada. And instead of doing for a generic type T, which has a lot of edge cases, we're just going to do it for I32. And this might be the attempt. We have a slice. It's a reference to a mutable slice. We have mid usize. Okay, that's going to be the point that we want to split it at. And then we want to return 2 references to the slice, at those points. So something we might try is get the length of it, assure that the length is longer than the point we're trying to split it at, and then return a tuple of the first part and the second part. And they say this is not going to work. And I'm just going to scroll down to see why. This function first gets the total length of the slice. Then it asserts that the index given as a parameter is within the slice by checking whether it's less than or equal to the length. The assertion means that if we pass an index that is greater than the length to split the slice at, the function will panic before it attempts to use that index. Okay? So going back here, they're saying that this will panic if that assertion fails. That makes sense. Then we return 2 mutable slices in a tuple, one from the start of the original slice to the mid index, and another from the mid to the end of the slice. When we try to compile the code in listing 19-5, we'll get an error. And the error is cannot borrow slice as mutable for more than once at a time. First mutable borrow occurs here. Second mutable borrow occurs here. Oh, so the issue is we're trying to borrow the slice at 2 different points, but it's still the same slice twice in the same scope. That we're not allowed to do that. You're only allowed to have one mutable borrow at a time. Okay. Rust borrow checker can't understand that we're borrowing different parts of the slice. It only knows that we're borrowing from the same slice twice. Borrowing different parts of a slice is fundamentally okay because the 2 slices aren't overlapping. But Rust isn't smart enough to know this. When we know code is okay but Rust doesn't, it's time to reach for unsafe code. Listing 19-6 shows how to use an unsafe block, a raw pointer, and some calls to unsafe functions to make the implementation of split at mute work. And seeing it here, we now implement standard library slice. Okay, so the signature is still the same. We still get the length. We create a pointer to the slice. a mutable pointer. We assert the length, and now we do slice from raw points, slice from raw parts, mutable, and then we have the pointer to the slice, and then we have the midpoint, and then we do an offset for the second one. Pointer, offset, mid as eye size. Mid is eye size now? Or is it that this pointer is an eye size? I don't know. I'm only going to know until afterwards. After I put this into my editor. And then we do length minus mid. So I understand why this works, but still, let me put this in my editor to see if it might give me some clarity on things. This is just a new function. As such, you can just go at the top. So yeah, let's make this a little bit bigger. We have a pointer reference to the mutable. So it's a location. That's probably what I wasn't really getting earlier. This may be a mutable, but the reference to the location is not mutable. So that's why this is immutable, the PTR, the pointer. Okay. Now that's sunk in, let's continue onward. Length is usize, which, yes. From raw parts, mutable takes data. So I'm guessing this is a pointer to data. Oh, offset. Offset has to take eye size and not U size. That makes sense, because mid is initially U size. But I guess this count must take an eye size, and that's why they casted it. Okay. And pointer offset. So this should start from, oh, that makes sense. Okay. So the first line, right? We're going from the very beginning, there's no offset, to the midpoint. At the second line, we're going from the offset, which is the midpoint, to the end. Here is the length parameter. So the length is always going to be the same. Well, not necessarily the same, but the length is just the distance between the end, from the mid to the end, which they gather here. And they put that as the length. So from the offset down to the end is how they get to the end of the slice. Alright, so now that makes sense, we can make this smaller and go back to the document. Recall from the slice type section in chapter 4 that slices are a pointer to some data and the length of the slice. We use the length method to get the length of the slice and the as_mut pointer method to access the raw pointer of the slice. In this case, because we have a mutable slice to I32 values, as_mut pointer returns a raw pointer with the type *mut I32. Those are raw pointers? Hold on. So this returns a raw pointer. I see. So that type is a raw pointer, but it's immutable? Let's continue reading. We use the length method to get the length of the slice as the as_mut pointer method to access the raw pointer of a slice. In this case, because we have a mutable slice to I32 values, as_mut pointer returns a raw pointer with the type *mut I32, which we stored in the variable pointer. Okay. I see. So outside of the unsafe block, we created a raw pointer, which they discussed that we're allowed to do. We keep the assertion that the mid index is within the slice. Then we get to the unsafe code. The slice from raw parts mut function takes a raw pointer and a length, and it creates a slice. We use this function to create a slice that starts from pointer and is mid items long. Then we call the offset method on pointer with mid as an argument to get a raw pointer that starts at mid, and we create a slice using that pointer and the remaining number of items after mid as the length. So reading it is kind of confusing, but they're just explaining this part here, which we already went over. The start location of where the slice is and the length that we're going to. And this is the start of this location where the slice is. So we see the slice, we do an offset to get to the midpoint again. And here we're just calculating the length of what's left over and then passing that into the length parameter, which you can't see it here, but in the editor, it was at the argument. The function slice from raw parts mute is unsafe because it takes a raw pointer and must trust that the pointer is valid. The offset method on raw pointers is also unsafe because it must trust that the offset location is also a valid pointer. Therefore, we had to put an unsafe block around our calls to slice from raw parts mute and offset so we could call them. By looking at the code and by adding the assertion that mid must be less than or equal to length, we can tell that all the raw pointers used within the unsafe block will be valid to data within the slice. This is an acceptable and appropriate use of unsafe. Okay, so what they're stating here is that when we look at this, we can tell this is an appropriate use of unsafe because of how it's written. We know that the midpoint is always going to be within the slice. As such, we also know that the calculations for length and midpoint are also going to definitely be within the slice. So the only thing we don't know at this point in time is if the pointer to the slice is valid. But I think we know that as well because the slice that was passed in, assuming that the slice that was passed in was valid, and given that it's coming from safe rust, it should be, then creating a raw pointer off of it should be fine as well. And thus, that is all of the parts that could be unsafe, which are the pointer and the offsets dealing with the pointers to this memory block, we can guarantee are safe. And thus, this is wrapped in a safe block, and we know it's not gonna, the worst thing you can do is panic. That's because you passed in a midpoint that's greater than the length. Your fault. And also, if I recall correctly, things like this, the panic should be documented so that you should be able to read it and understand that this function call could panic if you pass in the wrong thing. Note that we don't need to mark the resulting split at mute function as unsafe. And we can call this function from safe rust. We created a safe abstraction to the unsafe code with an implementation of the function that uses unsafe code in a safe way. Because it creates only valid pointers from the data this function has access to. They're just harping on the point that the things that we return are not unsafe. They are safe. And their reasoning was, where is it? Because it only creates valid pointers from the data this function has access to, which I stated earlier, that we passed in a slice. If the slice is coming from valid Rust code or safe Rust code, then that pointer should be good. And then we already did assert for the midpoint. So given that the midpoint is definitely within the length of the slice, then we're golden there as well. So everything that we're passing back, like the returning thing, this slice and this slice, it's just regular code at that point. No need for unsafe. In contrast, the use of slice from raw parts mute in listing 19.7 would likely crash when the slice is used. This code takes an arbitrary memory location and creates a slice 10,000 items long. standard library slice, arbitrary location memory, makes a raw pointer out of it, and then within unsafe block tries to make a slice that is that long. And that should definitely fail. Well, it shouldn't definitely fail, but it should fail in a lot of cases because there's no guarantee that that point of address has that much space after that we could just use for a slice. Some of that location might be used for something else already. We don't own the memory at this arbitrary location, and there's no guarantee that the slice this code creates contains valid I32 values. Attempting to use slice as though it's a valid slice results in undefined behavior. Yeah, that's another thing. The space that it's taking up, the space that it's referencing now, there's no guarantee that the data within that space is I32, which they mention here. Using extern functions to call extern code. Sometimes your Rust code might need to interact with code written in another language. For this, Rust has a keyword extern that facilitates the creation and use of a foreign function interface, FFI. An FFI is a way of a programming language to define functions and enable a different foreign programming language to call those functions. Listing 19-8 demonstrates how to set up an integration with the ABS, which I believe is the absolute function, from the C standard library. Functions declared within extern blocks are always unsafe to call from Rust code. The reason is that other languages don't enforce Rust rules and guarantees, and Rust can't check them, so responsibility falls on the programmer to ensure safety. I see. So we have extern C, and it looks like this is just mapping to the absolute value. And we're saying that the input's going to be I32 and the output's going to be I32. But that probably exists in C. I don't know how they're going to like reference it, whether it's going to be like dynamically linked or statically linked. That part I don't know. But it looks like we could do main unsafe print and then use the function call as long as it's within unsafe, which they explain the reason why, because everything extern, all extern blocks are unsafe, and as such you need to call them seemingly within an unsafe block or within an unsafe function. Within the extern C block, we list the names and signatures of external function from another language we want to call. The C part defines which application binary interface, ABI, the external function uses. The ABI defines how to call the function at the assembly level. The C ABI is the most common and follows the C programming language's ABI. Okay. So ABI, application binary interface, which is just the rules of how to interact with the binary of that language. And marking it as C lets Rust know that we want to use C's ABI. I'm kind of curious now if I can run this without doing anything extra, because earlier I was worried about like linking and whatnot, but that may not be an issue. And run. It's not an issue. I could just arbitrarily do this with C. Wow. That's nice. I thought there would be a lot more ceremony to it. Cool. Calling Rust functions from other languages. We can also use extern to create an interface that allows other languages to call Rust functions. Instead of an extern block, we add the extern keyword and specify the ABI to use just before the function keyword. We also need to add a hashtag no_mangle annotation to tell Rust compiler not to mangle the name for this function. Mangling is when a compiler changes the name we've given a function to a different name that contains more information for other parts of the compilation process to consume but is less human readable. Every programming language compiler mangles names slightly differently. So for a Rust function to be nameable by other languages, we must disable the Rust compiler's name mangling. In the following example, we'll make the call from C function assemble from C code after it's compiled to a shared library and linked from C. So here they're just going over the opposite direction. If you want to call Rust function from other code, from other languages, or from within other languages, and they're going, since we already did calling C code in Rust, now we're going to call Rust code in C. In order for us to set that up, we would have to write something like this, where we have, it's public, that seems mandatory, extern to know that it's going to be using unsafe code and it's going to be needed the ABI of another language, C stating that we're going to use C's ABI, and they mentioned the no mangling so that the compiler doesn't change the name of this, because if it changed the name of this, we wouldn't know how to call it from C. Call from C is the name of the function, takes 0 parameters, and it just prints this line. This usage of extern does not require unsafe. It seemingly doesn't require unsafe because we're not using it in Rust code. This is meant to be compiled and then not called in Rust at all. One thing they did mention, which is one of the things I was worried about earlier, was this after it is becomes a shared library and linked from C. So you do have to still create a shared library, which I believe is a .so file, shared object, and then you have to link it. So you would have to know how to do that in C. Accessing or modifying a mutable static variable. Until now, we've not talked about global variables, which Rust does support but can be problematic with Rust ownership rules. If 2 threads are accessing the same mutable global variable, it can cause a data race. In Rust, global variables are called static variables. Listing 19-9 shows an example declaration and uses a static variable within a string slice as a value. Okay, so Rust does have globals, and I should have guessed that it's static because static, at least from what I remember. Oh, wait, that was a different static. I'm thinking of static for strings, where if you use the static keyword, then that string is written directly to the binary, and thus it's available at any point of your code, at any point of your binary. So you can just call it whenever. But I guess it's a similar principle. So we have static here, hello world, and it's a string. And then we call hello world. Static variables are similar to constants, which we discussed in the difference between variables and constants section in chapter 3. The names of static variables are in screaming snake case by convention, and we must annotate the variable's type, which is a reference static string in this example. So this is exactly like the example I was thinking of, but let's continue reading. It might be slightly different. Static variables can only store references with the static lifetime, which means the Rust compiler can figure out the lifetime. We don't need to annotate it explicitly. Accessing an immutable static variable is safe. Alright, so this is exactly what I was thinking of, because I was thinking of the lifetime section where we had to use static. And it seems as though when you write the static keyword, that is automatically going to give it a static lifetime, which, if I recall correctly, just writes it to the binary and you always have access to it. And as long as your static variables, which in this case could be global variables, are immutable, then it's safe because it's never going to change. Constants and immutable static variables might seem similar, but a subtle difference is that values in a static variable have a fixed address in memory. Using the value will always access the same data. Constants, on the other hand, are allowed to duplicate their data whenever they're used. Oh, that makes sense. So static has one memory address location always, whereas constants can be duplicated and like replicated in other different places. So the point of reference when you're looking at a constant may not always be the same. Another difference between constant and static variables is that static variables can be mutable. Accessing and modifying mutable static variables is unsafe. Listing 19-10 shows how to declare, access, and modify a mutable static variable named counter. Oh, you can have mutable static variables. I see. And then if you want to access it, you might have to do it within an unsafe block. That is curious. That is very curious. And then main. Yeah, this is probably something you should never use, but is an option. As with regular variables, we specify mutability using the mute keyword. Any code that reads or writes from counter must be within an unsafe block. This code compiles and prints counter 3 as we would expect because it's single-threaded. Having multiple threads access counter would likely result in data races. With mutable data that is globally accessible, it's difficult to ensure that there are no data races, which is why Rust considers mutable static variables to be unsafe. Where possible, it's preferable to use the concurrency techniques and thread-safe smart pointers we discussed in Chapter 16, so the compiler checks that data access from different threads is done safely. Implementing an unsafe trade. The final action that works only with unsafe is implementing an unsafe trade. A trade is unsafe when at least one of its methods has some invariant that the compiler can't verify. We can declare that a trade is unsafe by adding the unsafe keyword before trade and making the implementation of the trade as unsafe too, as shown in listing 19-11. So yeah, a trait is unsafe if a part of it, any part of it, is unsafe. The compiler can't verify it. And then you note that by using the unsafe keyword. So unsafe right before the trait name, or a trait keyword, and then you have the name. And then if you want to implement it for, say, I32, you do unsafe, implement, name of the trait for, and then the thing that you're doing it for. By using unsafe implement, we're promising that we'll uphold the invariance that the compiler can't verify. As an example, recall the sync and send marker trait we discussed in the extensible concurrency with the sync and send traits section in Chapter 16. The compiler implements these traits automatically if our types are composed entirely of send and sync types. If we implement a type that contains a type that is not send or sync, such as raw pointers, and we want to mark that type as send or sync, we must use unsafe. Rust can't verify that our type upholds the guarantees that it can be safely sent across threads or accessed from multiple threads. Therefore, we need to do those checks manually and indicate as such with unsafe. Oh, that is a very valid use case. So yeah, in Chapter 16, they were talking about send and sync and how most things, all the things by default, with the exception of, I guess, unsafe, implement send and sync, so you don't have to do anything. However, if a part of your code is not send or sync, for the most part, you would have to put that in an unsafe block if you still want to try to use it in the send and sync ways. Because at that point in time, Rust can't validate, the Rust compiler doesn't know whether or not it's safe to send in concurrent matters, or use concurrently. But if you can guarantee that yourself, and you're confident that you can guarantee that, then by all means use an unsafe block. When to use unsafe code. Using unsafe to take one of the 4 actions, superpowers, just discussed isn't wrong or even frowned upon. But it is trickier to get unsafe code correct because the compiler can't help you uphold memory safety. When you have a reason to use unsafe code, you can do so, and having the explicit unsafe annotation makes it easy to track down the source of the problem if they occur. And with that, that is the end of this section. That was very, very informative. Unsafe code is no longer as scary as I thought it would be. It actually makes a lot of sense. Well, if you like the video, hit like, subscribe. Aside of that, see you next time. Peace.